To have the opportunity of hosting a talk by Professor Hart in the Foundation seminar series. But this is one of the cases where the introduction of the speaker would take half of the talk, in fact, if I had to say everything. So I try to be short. So Professor Hartle is a research professor and professor of physics emeritus at the University of California, Santa Barbara. He's been founder and former director of the Institute of Physics at Santa Barbara, indeed, and he is a member of the U.S. Academy of Sciences. And in the past, he gave pioneering contributions to quantum cosmology and quantum foundations. And I think everyone knows about the theory of consistent histories developed by Professor Hartle in collaboration with Gell-Mann, and about the study on the universal wave function done by Professor Hartle in collaboration with Stephen Hawking. So today's talk will be about foundations, indeed, I think, and the title is Quantum Mechanics with Extended Probabilities.
Thank you very much. Well, we'll see how foundational it is. As far as I know, consistent or decoherent histories quantum theory is the only formulation of quantum mechanics that we have today that is logically consistent, consistent with experiment as far as is known, general enough for cosmology, consistent with the rest of modern physics, such as field theory and general relativity, and generalizable to, at least at a semi-classical level, to quantum gravity. It may not be the only theory of these that has these properties. And therefore, it's interesting to look for generalizations and alternatives to quantum mechanics. And by quantum mechanics, I mean laboratory quantum mechanics, or what I will call Copenhagen quantum mechanics. This is certainly necessary for cosmology, because laboratory quantum mechanics talks about the outcomes of measurements, assumes there's a classical world, and none of these features do we have in the beginning of the early universe, when there were neither measurements going on or observers around to deal with them. So some sort of generalization is necessary. Decoherent histories is one of those. It's also desirable for experiment. If you have attractive and competing theories, then that helps motivate experiments. But the project of finding generalizations has proved that it is quite difficult. As Steve Weinberg said, it's striking that so far it has not been possible to find a logically consistent theory that is close to quantum mechanics other than quantum mechanics itself. There may have been progress here. I looked on the schedule, and there'll be a talk about this tomorrow, right? So I may have to revise this, but that's the way it seems right now. So my talk today is an extension of decoherent histories quantum mechanics to provide a different starting point for looking for generalizations and alternatives that involve some extended theory of probabilities. What I'm looking for in this group is some pushback. Right? I'm not so sure this is completely consistent, and I'd like you to sort of, I'd like your strongest possible criticism. Well, we have to start, if we're going to talk about extended probabilities, with a little discussion of probability theory. I'll take the point of view, I guess, that originates with Di Finetti in the 30s, that probabilities are instructions for betting. That is, asserting that the probability of an event A is P, it means that if some bookie offers you a payoff S if A occurs, you'll put up P times the stake S and regard it as a fair bet. In this particular framework, P can be positive and S or negative, and S can be positive or negative. S being negative just means that instead of the bookie paying you, you pay the bookie, which is not generally a good thing, but it's a symmetry between the bookie and the bettor. What Di Finetti showed is that all the rules of probability theory follow from the requirement that it not be possible for the bookie to offer you stakes which make what's unfortunate for international relations called a Dutch book. That is, a bet in which you're sure to lose. Not statistically, but every single time. And in particular for that, probabilities have to be positive. So you can see that, just from a simple example. Suppose you would bet on events A and not A, whether A occurs or doesn't occur, and you have probabilities PA and P not A, and the bookie is going to offer you, knowing what your probabilities are, is going to offer some stakes, SA and SA bar. Your gains are then going to be the following. There's the stake, that's what the bookie will pay you, and what you put up is PA times SA, and PA bar times SA bar, and there's subtractive loss, because that's what you put up. This is your gains. The gains for A bar are in a similar form. Now, suppose PA is less than, your probability is negative. Then the bookie can pick stakes SA, which is negative, and let's suppose the bookie decides not to pay off if it doesn't occur at all. Then the gains are, and what you think is a fair bet, 1 minus PA times SA, which is negative. That's negative. And if it doesn't occur, it's minus PA times SA, which is minus times your negative probability times another minus sign. Both gains are negative, and so you lose. Always. So it's not a good idea to have negative probabilities on things. From this point of view, a physical theory is just a tip sheet. It's a way of providing particularly reliable betting strategies for alternatives in the universe. So, for example, if we throw a cat and a cannonball and an economics textbook off the top of this building, Newton's law of gravity, plus other things, provides you with a way of explaining how you should bet on what time they reach the bottom of the building. Physical theories, therefore, are instructions for betting on the regularities of the universe. We identify the regularities, encode them in theory, and then can bet on them in further situations. That's true, for example, even if Newton's law of gravity holds, even if you drop something off your tower here on Earth, or somebody on the planet Zargon is throwing similar things, they will fall to the ground in the same way. So far, so good, but the Di-Finetti derivation of the rules of probability assumes that all the alternatives that are describable by the theory are the basis of a settleable bet. The bets aren't settleable, of course, there's no problem. But quantum mechanics provides alternatives that are not the basis of settleable bets. And nowhere is that more clearly illustrated than in the famous two-slit experiment. If you have an electron gun, a screen with two slits in it, the upper hole and the lower hole, and the electron proceeds toward a screen where it's detected at Y, you get the characteristic interference pattern at Y. And then if you want to decide, two alternative histories of whether the system went through the upper slit or the lower slit, as is well known, it's not possible to settle a bet on whether it went through the upper slit or the lower slit, because if you did so, you disturb the system, the interference pattern is destroyed, and you have a different system to talk about. That's because these alternatives are interfering in a quantum mechanical sense. So non-settleable bets present a choice. You can either assign probabilities only to alternatives that are the basis of settleable bets in principle. That's decoherent histories. You have a decoherence condition that restricts what sets of alternatives assign probabilities. For example, you wouldn't assign probabilities to the two-slit experiment because those are interfering alternatives. Or you can extend the notion of probability and assign extended probabilities, which therefore don't have to satisfy the rules of probability theory. In particular, they don't have to be necessarily positive to all the alternatives. And it's that what I'm going to, which I'm going to examine in this talk. So extended probabilities I'll take to be, they satisfy the usual rules of probability theory, but they're not necessarily positive or less than 1, and for non-settleable bets.
Yes, as a rule of betting, what would be the notion of probability when you have non-settleable bets? What would be the reason for?
What would be the, what would be the definition of probabilities when you have non? You define probabilities as the,
As I define probability.
as the rule of betting.
Right.
So now that you have a non-settable bets, what's the definition of probabilities?
Well, we're going to have a theory which generalizes quantum mechanics, which includes those non-settable bets. If you lie, it's going to incorporate a notion of probability that properly recognizes in quantum mechanics that there are alternatives you can't find out there. So it assigns numbers to those. So it would be a more unified. You would have to judge for yourself, I think, whether you think this is useful.
But you can't have an extension of the definity rule.
Sorry.
You don't have an extension of this definity rule of betting.
I'm just a little. I don't have
The rule for betting that made probabilities positive. He's asking, do you have an analogous rule here?
I will show you, right, when probabilities are settable, they have, in a very general sense, they, when bets are settable, they have positive probabilities. But you need a little framework first. So the answer is yes.
Maybe I can just ask a related question. What is the reason for satisfying the usual rules, except for the range, when you have a non-settable bet? Can you motivate that?
Oh, that's just conservatism on my part, right? I mean, I think you could abandon them all, right? But we get a convenient sort of story this way, so I'm not claiming generality here.
And those usual rules are things like that they add up to 1?
Yes, for example, an example of the usual rule is the probabilities still add up to 1.
Okay, and Bayes' rule is another one? Or?
Yes, Bayes' rule still works, right? All that probabilities of exclusive things, they add up. The only rule we're modifying is this rule of positivity.
Okay.
So a negative probability, or one bigger than 1, is also an instruction for betting. Don't bet on this, because we're not going to. You're not going to settle it. If you do, the bookie can propose a Dutch book, and you'll lose a lot of money. If you imagine that. So it's all part of instructions for betting. I'm going to, as convenience, I'm going to stop saying negative probability or 1 bigger than 1 and just say negative probability for the rest of the talk. It turns out, in the interesting cases, that very few probabilities are bigger than 1. Now, negative probabilities show up in quantum mechanics all the time. It's been observed by many people over the years. The most prominent example is perhaps the Wigner function. This is a function of x and p, right, constructed in this way by Wigner. If you've got a state psi, and you construct the Wigner distribution, and this is not generally positive. Positive sometimes, negative powerful. It does correspond to non-settable bets because x and p are usually said to be non-simultaneously measurable, and therefore you can't have a settleable bet on what the argument is. If you coarse-grain the situation, that is, follow either x or p, those are settleable bets, and the probabilities produced by the Wigner functions, marginalizing over them, are positive. In fact, Feynman was so impressed by the number of times you get negative probabilities in quantum mechanics, he wrote a whole very nice essay on negative probabilities in quantum mechanics, just listing the cases where you get something that looks like a negative probability showing up naturally in quantum theory. So he said a physical theory just because it has a negative probability is not necessarily incorrect. The possibility is that it might not correspond to a situation which can be verified. And that's very much the point of view which we'll take in this talk. So I'm now going to describe for you a model cosmology, right, in which we will have negative probabilities and show you what the connection is to the usual ones. So for my model, I'm going to consider a large box.
And find the probability for some things is negative. Then I should not make any bet on anything. Right? I can't be selective.
There's one negative probability in the set.
Then don't bet at all.
Because the bookie gets to pick
the bad one. Right. Okay. So in practice,
if you talk to social scientists, like economists, no problem. They get negative probabilities all the time.
Where did they go wrong?
It might be the same reason.
I mean, not verifiable. Let's not go any further. It's being recorded after all. Okay, I'm going to consider a large box, maybe 20,000 megaparsecs on the side, right? And everything is in it, right? We're talking about elaborate quantum mechanics here, right? The observers, everything are inside the box, a closed system. What I'm neglecting is gross fluctuations in the geometry of spacetime. That is, I'm neglecting quantum gravity because by doing that, the usual apparatus of Hilbert space, states, and all that stuff is clearly applicable and can be applied. So if you like, you can think of it as just a box, big box of large box of particles. The theoretical inputs to this are going to be the Hamiltonian of the closed system and its quantum state, which I assume are supplied by theory. Some sort of string theory of the Hamiltonian, the wave function of the universe, let's say for this. Now, what you hope to get out of this, the most general objective for any quantum theory, is the probabilities of, or the extended probabilities in this case, for the members of sets of alternative coarse-grained histories of the closed system. So, for example, we might be interested in the orbit of the Earth going around the Sun. What's the probability for that? We hope, in any reasonable theory, the probability is high for a Keplerian ellipse. But in quantum mechanics, you can take any orbit around the Sun. Those orbits are typically coarse-grained because we're talking about the center of mass of the Earth and not of the other 10 to the 80th visible particles in the visible horizon. We're not talking about this center of mass for arbitrary precision, because if we did, right, then you'd pick it into a momentum having stayed in the place, it would certainly be lost. And typically, we're not talking about it at each and every time to a Planck time along here, but at some discrete set of times as we go along the system. That's what we mean in this simple example by coarse graining. A fine-grained history would follow the center of mass exactly, right, at each and every time. So, to define an extended probability quantum theory, I need to do two things. One is I need to give you a description of the sets of fine and coarse-grained alternative histories, which are the targets of extended probabilities, and then a prescription for assigning extended probabilities to each of them. So, first of all, some standard stuff about histories. Histories are composed, we'll take it, of alternatives at one moment of time. Alternatives at one moment of time are represented, we take an exhaustive set of exclusive alternatives at one moment of time, and these are represented by sets of, I'll be working on the Heisenberg picture projection operators, yes or no. So if you have a region of space, for example, you ask, is it in region 11? Yes or no. That corresponds to a projection operator P11 at time t. The operators are orthogonal, showing that they represent exclusive alternatives, and they sum to 1, showing that they're exhaustive, and they evolve in time. This is where the Hamiltonian comes in by the Heisenberg equation of motion. So one-dimensional projections are fine-grained. There's projections on one basis, basis vector in the Hilbert space, and all the other ones are coarse-grained. Okay, that's alternatives at one moment of time. Histories are specified by a sequence of sets of alternatives at different moments of time. Is the particle in this region? Yes or no. Is the particle in that region? Yes or no at a later time, and so on. So they're specified by sequences of sets like this. So this indicates that the set might be different at different times. Position at this time, momentum at that time, and so forth. And an individual history is represented by a particular sequence of alternatives. Yes in this region, no in that one, yes in this region, no in that one, which is represented by the chain C alpha of all those projections. Well, I already said this, fine-grained. Coarse-grainings of sets of histories, as far as the class operators, as these are called, goes, is just what a coarse graining means is you take your set of histories, C alpha, and you bundle them into bigger classes, and then the chains are just sums. So if you have, if alpha bar is a coarser partition of, is a coarse graining of the sets of histories, then every history in alpha is in some set alpha bar, and C of alpha bar is just the union of all the classes that contain it, and the class operators are sums in those classes. Okay, so here's the theory. The assumed input is the Hamiltonian and the state. The histories are these chains of projections. Then I'm going to assign numbers I'll call extended probabilities by this formula. We take the expected value of the chain in the class operator represents the history, and I take the real part. This is not generally positive because these are not positive operators, although it does agree with ordinary quantum mechanics if your histories consist of one moment of time, because then you just have the expected value of the of a projection operator, which is always positive. The sum rules, the probability sum rules, are all satisfied exactly, right? Because in a coarser grained set, right, the chains are sums of the finer grained members of the set, and the p alphas are therefore, because this is linear, right? These are satisfied. Just linearity shows you that the extended probabilities in the coarser grained set are the sums of the extended probabilities in the finer grained set. This formula was used by Goldstein and Page for linear positivity. Their condition was yet another decoherence condition, that this just be positive. I'm just going to take it for all history. So every single history we have, we assign this as a probability.
Deviate from ordinary quantum mechanics here just by taking the real part? Is that?
This is probably what you're thinking of as real quantum mechanics, that's preserved. But we're talking about histories which are chains of projections, sequences of things in time, the rules for those. And the C's are not themselves projections, because the product of projections is not a projection. So you have to ask, what's the real quantum mechanics from which I am deviating? Okay, that's decoherent histories quantum mechanics. But rather than explain that to you up front, I'm going to get it out as a certain limit in the back, and then you'll see what the standard story is. We're deviating from evolve, reduce, evolve, reduce, evolve, reduce, if you want. This formula is not true in usual quantum mechanics. Exactly. It's related. As I'll show you, if the sets of histories are decoherent, this is the formula. Well, also that. Anyway, it's different from ordinary quantum mechanics. No measurement. This is a closed system.
If there were a measurement at time t1 described by the set of projectors, the first set, the one you associate, and if there were a measurement at time t2 described by your second set of projectors, then this formula would specify what the probability of getting outcome alpha 1, then alpha 2, then alpha 3.
Yes.
And it's called the Wigner formula typically. So it's quantum mechanical in that sense, but here's my question. There's many more alternatives for generating joint probabilities that will reproduce the Born statistics at every time. So why choose the Wigner formula, given that these aren't measurements? There's an infinite class of these things.
Oh, you are talking about further generalizations.
Yes.
Great. Please do something for it. I'm trying the simplest possible thing I can think of. Okay, just by way of example, here's the two-slit experiment again. So I just calculated what, for example, this extended probability from this formula would look like for going through the upper slit. I think that's what this is. And you'll see it's sort of more. There's more p going toward the upper slit, right? But then we run into negative ones down here. For going through the lower slit, it looks the other way, symmetrically, and if we add them up, that is coarse grain, the upper slit and the lower slit, we get the standard interference pattern, which is positive. The probability of arrival y is indeed positive. We can do the coarse graining another way by, let's just consider the probability if we're going through the upper slit, and we'll combine these regions into bins, not just ask for each y, that is each position on the screen, but put them in bins. So here we are with some small bins, and you can see already that well, we still have a little negative probability down here. But if you take a coarse enough bin, then you get all positive probabilities. That is not the point at which the interference pattern vanishes. There is still some remnant of it here. So you can assign positive probability. There's an interesting region in which things are not decoherent, but still have probabilities that are positive, which in principle, if you knew how to do it, you could assign settlable bets. So appropriate coarse graining can make these extended probabilities positive. Yes?
Question that goes into making that first plot?
This one. I just took EDIS, right, from going through here, right, and then I calculated the real part, right, that it went through here. That's the first part of the history, and then it arrived at y. And
It's just real part of it to the IS. Is that
so it's this. It's calculated this.
okay.
See, it's much simpler in this case. You just do it from wave mechanics. It goes through the upper slit. That's the first part of it. The history only has two pieces. Right? Upper slit and arrived at y. Right? And note that's given by letting it go through the upper slit and calculating the wave that emerges through the upper slit and then taking the real part of the wave when you get to the surface. Oops. So how negative p is a measure, rough measure of how much coarse graining is needed to get the probabilities positive. So the more negative p is, the harder it is when you give an example of coarse graining to get it positive. Another example here is this is called the three-box example. I believe it's due to Aharonov and Weidman for another purpose, so it's a very useful example. Let's consider a single particle that can be in one of three boxes, A, B, and C. And the Hamiltonian I'm going to take to be 0 for simplicity. And we're going to assume that the initial state, the psi in this problem, is that the particle is symmetrically likely to be in A, B, or C. So these brackets mean, this state means the particles in A, this one means the particles in B, and so forth. I'm going to pick a particular final state following these people, phi, which is A plus B minus C. And I'm going to ask the following question. Given that the particle is in the final state phi, what's the probability that it was, that is a historical question, in box A, B, or C? So this is a famous example in intermediate time, but let's see how it works out with these extended probabilities. So we introduced the projectors. For example, a projector on A is just A back to back. Not A is 1 minus that. Projector on phi is phi back to back, and so forth. So the histories that are involved here, there are three possible histories. You go from psi, it was in A, it winds up in phi to B. I think this is Raphael Sorkin's three-slit experiment, right, which he likes to talk about all the time. And so here are the chains corresponding to those three histories: A, phi, B, phi, C, phi. And then we just calculate first the joint probability for A and phi, which is given by that. And then the conditional probability for, given that phi happened, right at the end, what was the probability earlier, what was an A? And here are the extended probability. 1, 1, and minus 1. So already you see, A, B, or C. Now let's consider coarse graining. I'll just do one. I guess I'll do them all. We can coarse grain and ask not the question whether it was in box A, B, or C, but ask whether it was in box A at the earlier time and in B or C. That is, we coarse grain by joining these, considering these histories in one class, which is not A. And you do the similar for B and C. Then you find the following. The probability, if you do that, then you do get positive probabilities. You can bet the probability was that it was in A is 1, and not in A, 0. The probability that it was in B is also 1 by symmetry, and 0. That's not a contradiction because you can't check that if it was in A, then it was not in B. The probability for C is just the loser. It's negative and greater than 1. So the probability to be in A is 1 is distinct from not A, and B is 1, but that's not a contradiction that can't be settled. If it's in A, then it's not in B. That's a sort of in-your-face example. You know what's going on. Okay, now that's enough of the framework. Are there any questions about that?
So I'm accustomed to seeing the negative probability appear in the three-box paradox only when weak measurements are assumed. You're assuming these strong measurements.
No measurements.
Oh, that's right, no measurements. But the formula you're using is the formula that I would use were I to do a measurement. And so, can you just take me through how you get probability of C given phi equal to -1?
Let's do that afterwards. It's just, given this and given these states, we can calculate all these matrix elements, and then we calculate conditional probabilities in the usual way from the joint rings by dividing for the probability of phi, which is the sum of...
Right, but given that you're using the Wigner formula, the probability of C and phi has got to be positive, the probability of phi has got to be positive, so I don't see how you can get a negative value using Bayes' rule.
But I think this comes from the description of the real path.
I think we haven't not started doing this afterwards, especially because it's a well-known theorem that your IQ drops by 40 points every time you stand up. You're liable to make a mistake, and then possibly make a mistake.
So the point of this example is coarse graining here doesn't help.
Coarse graining does help because you things you can bet on. Right.
Oh, I'm sorry, I misunderstood. I thought you said that there's
well, it doesn't help with C.
Yeah, that's what I meant.
But these are okay.
Sorry?
These are okay. Of course, it's a little bit hard to, can't do further checks. This is a historical question about whether it was in the past. It was one that
But it doesn't help with C.
It does not help with C.
Yeah. It helps with A and B.
Sorry?
It helps with A and B. So if you set the bet on A.
Well, A or not A, B or not B, but you still don't have the possibility of betting on A and B.
I mean, I think that's what everybody said in one way or another. Right? Can't go back too many times, otherwise you'll have to endure, this. All right. Now I'd like to come to
a better idea of what we might mean by a settleable bet. That's the theory, right? But to complete it, I want to show you that if we have a natural notion of settleable bet, we cut back to ordinary quantum mechanics for a very wide class of situations. And this is the case when we have sets of histories that are recorded. Every bet, in principle, or anyway, people that don't specify a prescription for how to settle a bet usually wind up in some sort of social trouble. Right? So a record of the outcome is one way of settling the bet. So I'm going to say a set of histories is strongly recorded if there's an exhaustive set of exclusive projections R such that they're exactly correlated with the C's. They come at the end of the C's, and so R alpha C alpha beta is 0 if we don't have C alpha, and is equal to C alpha if we do. There's then, as it says here, a correlation between the histories and their records between alpha and beta. This is given by alpha, beta, p beta. And so you can read off the probabilities for the histories from the records, right, just as well as calculating from that formula. Now, that's a very general notion of recorded. Individual bettors will want to make very specific contributions, requirements on records, that they're in a certain set of variables, that is, they're in the Toronto Globe and Mail, right, or that the records last a sufficient length of time, or that they're accessible to both parties, measurable in a certain set of circumstances, for example, other situations. You can impose all those things, but they all fall into this very general and rather weak class. So recorded histories are the basis of settlable bets because, at least the probabilities are positive, because R alpha C beta, I'm just recalling the rule. If I sum this over beta, I get R alpha is equal to C alpha because the C's all sum to 1 in an exhaustive set of exclusive histories. And then if we calculate the probabilities, we calculate the probability of C is the same as the extended probability of R, which is positive. So extended probabilities are positive for recorded histories, and in that sense, bets on them are settlable. But recorded histories are also decoherent. Because if you have this relation, R alpha psi equals C alpha psi, which I'll define as the branch state vector alpha psi, then psi alpha psi beta is equal to this, R alpha R beta, but these are orthogonal projections, and so this is delta alpha beta is equal to C alpha, but that's exactly the decoherence condition. So decoherent histories, quantum mechanics emerges from this more extended framework if you restrict to recorded histories, which are certainly the basis of settlable bets. So this is the usual probability rule. Recorded decoherent sets have positive probabilities, and so we can say that decoherent sets have positive probabilities and bets on them can be settled. So thus, decoherent histories is a special case of this framework of quantum mechanics, just as Copenhagen quantum mechanics is a special case of decoherent histories. Here's a little comparison chart. We examine these, what are the probabilities, extended probabilities. In decoherent histories, you assign probabilities only to sets which are decoherent. In extended probabilities, you assign them extended probabilities to all sets. That means, for example, that you can ask what happens with fine-grained histories, with completely fine-grained histories. In general, they're not decoherent. So you won't get probabilities for them, but as we'll see in a minute, we will get extended probabilities for all fine-grained histories. The probability, some rules, are in decoherent histories theories, they're satisfied to the accuracy of the decoherence condition, which is some aesthetic problem for some people, right? But here they're satisfied exactly because of the linearity. What's approximate is records are correlated with the recorded approximately in decoherent history, as is every physically realistic record. It's not an exact statement, right? That the New York Times always gets it right. But they're only correlated approximately, right, in extended probabilities. So there's only some uncertainty in the theory, and this place is pushed off into what's meant by records. Settlable bets correspond to decoherent sets in decoherent histories, and settlable bets in extended probabilities correspond to recorded sets, and with the sufficiently general notion of recorded, these are one and the same. Any questions on this? Okay, I'd now like to put this all into in a sum over histories framework, because I'm going to make some philosophical comments at the end, and this will be useful to do that. So I'm now going to restrict to sum over histories quantum mechanics. So the fine-grained histories are Feynman paths, or field histories, if you like. Let's just imagine them as being particle positions. So we assign a particle position each and every time exactly. Coarse grainings are partitions of the sets of fine-grained histories, say, between two times, into exhaustive sets of exclusive classes. So if a particle is moving through layer, we could partition the sets of all the paths into the ones that move through this interval at this time, that interval at that time, this interval at that time. That would be a coarse-grained history. And the translation identity, it's just a mathematical fact, is that in any state, the expected value of the chain of projections corresponding to the coarse-grained history is equal to the sum over all the paths that lie in that class. So we sum over all the paths that actually lie in the class, e to the is, where s is the action for the system, divided by h bar. This is essentially in the Schrodinger picture, which is why the little hat, those are the Schrodinger picture wave functions. So the sum over histories formula for extended probabilities is just this. Using that, retranslate, it's the real part of psi, and then the expected value of the sum over history psi, a little formalism suppressed. So that means one way of thinking about that is that the theory is specified by giving a fundamental distribution for what the extended probabilities for the fine-grained histories are. W of Q of T is given by this. No integral here. We're talking about the exact paths. E to the I path multiplied by these endpoints. And so coarse-grained partitions are partitions of the fine-grained histories in the classes, and then you just sum over the basic distribution that you're given for the probabilities of whatever you get in the classes. What this means, that quantum mechanics can be thought of as a classical stochastic theory with a distribution that's valued in extended probabilities in a preferred set of variables, the sum over histories variables.
There's not an issue about normalization here. If you sum over all Q's, then you would like to have one, but...
Yeah, assuming the wave functions are normalized, that's true.
The integral over S, you know the factor that comes from the partition function?
Yeah, so this is really the density, of course, right? So if I sum that over all paths, here, that'll just give me the evolution operator from here to here, and then summing over the, well, because it'll give me the density. If I sum that over the final path, then I'll get one. Assuming I'm right, the states are normalized. Oops.
Why do you take the real part?
Pardon?
Why do you take the real part?
Well, I mean, it's probably conservative, but I somehow think the extended probabilities should be real and not complex.
So what's the role of the imaginary part?
I don't know.
Nothing known at this point in time.
Practically nothing is known about this.
That's just the ugly part.
I followed I don't know how to describe it. I took the steepest ascents path, the fastest route down to the bottom. Okay, this is hidden variables. Right? The hidden variables are the Q's. But it's not going to conflict with the Bell inequalities, because if you look carefully, they require positive probabilities in their derivation. These are extended probabilities. Local hidden variables, exactly.
Because non-local hidden variables are not in contradiction either with...
Right. Yeah. Thank you for that. Just to sort of compare the two theories, we're now getting classical physics, quantum mechanics closer to classical physics. We have we're going to fine-grained histories, or in the classical statistical mechanics, for example, I'll compare these to classical. They're a path in phase space E of t, obeying the equations of motion, and they're a path in quantum mechanics. We have paths in configuration space, Q of t, between the two different points. We can consider an ensemble of these paths, which we consider alternative phase space paths, and where we have an alternative configuration space path. We have betting instructions with probabilities, in the case of statistical mechanics, with extended probabilities in the case of quantum mechanics. We have a state, which is a distribution on phase space in classical statistical mechanics, and is given by the wave function, or that fundamental form, in quantum mechanics. We have a fundamental distribution, which is just in statistical mechanics that the probabilities of the completely fine-grained histories evolve according to the classical equations of motion, and are distributed by whatever your initial state is. And here we also have a fundamental distribution. Coarse grainings are partitions of the ensembles and the classes in both cases, and the probabilities are sums of the fundamental distribution over these partitions. Okay, now I'd like to talk about a word I don't usually use too much, and what this has to do with quantum reality. There's certainly a notion of reality in decoherent histories, quantum mechanics, but it's complicated by the fact that fine-grained histories are generally not decoherent, because you can't have a fine-grained history which is decoherence, because decoherence means ignoring something to get rid of the phases between them, and there you're keeping track of the phases of everything. And therefore, you have mutually incompatible decoherent sets for which there is no common decoherent fine-grained set, finer-grained set. That means you have different views, right, so to speak, mutually incompatible, but equally necessary views of the closed system. Well, people argue about what you should say in this case about what's real. Some people say you can say that there's one real history in each set. Other people say all the histories in the set are real. So without going into that debate, which I'm not very qualified to do, restricting the sum over histories variables, that is, restricting the variables, doesn't help with this, because if you imagine a box that has red particles and blue particles in it, you can't have a decoherent set which describes them both, but restricting to sum over histories of variables doesn't cut down the number of sets, because you can have a set where you follow the blue ones using the path of the red ones to ignore them, and vice versa. So there are at least two mutually incompatible sets, even in the case where you have sum over histories variables. It does help, of course, when you have fewer operators. So in decoherent histories, what you mean by reality is relative to the set that you use. So if you want to use ordinary English, it becomes complicated, because in principle, if you want to say something happened, you should say something happened in this particular decoherent set. A lot of people, it seems okay to me, but a lot of people. But this helps with that. We can pursue the basic method, which has been around in statistical mechanics for a long time, pioneered by J. Willard Gibbs, great American scientist. When we're interested in a system, we imagine that, for example, let's take a box of gas. The history is given by the positions and momenta of all the particles in the gas at all times. There's one real fine-grained history, we like to say. One particular, if we have a particular box of gas, there's one assignment. I'm talking classically now, position and momenta at every time. That fine-grained history has regularities in it, particularly the regularities that are given by the dynamical Hamiltonian. But Newton's law implies such regularities for these fine-grained histories, but they're not accessible to us. Right? There's no way of retrieving them and restoring them. What we're interested in are the coarse-grained regularities. And Gibbs's method, which was to embed the real history and ensemble conceptually in an alternative fine-grained histories, and then assign probabilities to them, so the coarse-grained regularities have high probabilities. The probabilities are then a measure of our ignorance of the fine-grained history. Or just to repeat this, the gas has one real fine-grained history, Z of t. Newton's law implies regularities of this history, but it's not possible to us in practice, certainly, and in principle, probably, to measure, store, retrieve, or compute with the information that's in them. Accessible regularities are highly coarse-grained, such as those that are summarized in the gas by the Navier-Stokes equations, for example, the approach to equilibrium, which are not certainly evident in the fine-grained. If we knew the real history, we could deduce those regularities from it, but we don't. So we use the ensemble method. And that is how it works here. There's one real fine-grained history Q of T. Fine-grained regularities, if any, are inaccessible to measurement. This time, genuinely inaccessible because they will have extended probabilities. We exhibit the coarse regularities implied by the real one by conceptually embedding in an ensemble of other histories. We can then use, this is the fundamental distribution, analogous, if you like, to the Gibbs distribution. And then we use the extended probabilities to bet on coarse-grained regularities when the bets, in fact, are settleable, accordingly. So from this point of view, extended probabilities are necessary measurements of ignorance of the regularities in the fine-grained histories. So
one real fine-grained history,
right,
as opposed to consistent histories where consistent histories theory,
Wait,
where it's like, with respect to a consistent set, there is one true one. With respect to another consistent set, there is again one true one.
That's right.
Now you're saying there's just one true one.
Right.
Okay.
Yeah.
I understood the basics. I'm good at that.
Okay, usual probabilities implicitly assume that we can find out in principle what the real history is. Okay, we use statistical mechanics books. They say, well, in principle, we can measure the position of the net of every single particle in the universe. But quantum mechanics requires a new level of ignorance to represent the true physical situation that there is no possibility of recovering that information. And those are the negative probabilities. It's also, by the way, impossible, I don't think there's room enough in the universe to write it down, to determine the real history of the 10 to the 8th particles in the classical universe, or even to write down its description. So it's somewhat of a moot point to say, in principle, we could go look at it, when in fact, it's probably genuinely impossible. Okay, well, there's some advantages to this point of view. It's closer to the classical idea of reality. No, there's just one thing. It provides a unified perspective on coarse graining. The unique fine-grained history is realized in one of any coarse-grained set. And that's the real one that happens. And it allows for, as I just mentioned, an interpretation of extended probabilities as measures of ignorance. Fine, okay. Well, this is just fine. But if you take this point of view, it's a starting point for generalization.
So there's still the freedom in the choice of a complete set of projection operators at each moment of time.
Well, I'm in cell over history, so I'm assuming, yes, we've done a particular set of fine-grained histories. So in order to get this point of view, I have to do two things, right? I mean,
so you're going to have to fix a preferred one at each time by some rule or some new law or something.
Well, we picked the natural one, right? So following fine. You know, we have fields in the case of field theory, geometries in the case of geometry, the space-time, but in principle it could be generalized.
Is your question that here you choose like to measure the Q's, but you could have measured the P's?
Well, he won't allow us to talk about measurements, but I could imagine this if we narrow ourselves down to time t. That at time t in your list of an exhaustive set of projection operators, you would have the position.
Yeah, but you could actually.
And I would say, aha, no, it really ought to be momentum. And so I'm asking what criterion says we're going to take position rather.
Once again, I just took the steepest route down, right? Since I know, some of our histories with momenta is possible, but you can't just do it with momenta. You can do it in phase space. But then the mathematical structure of the task gets complicated. Right? Discontinuous.
Oh, I see. So it's always position for you.
I think we're just doing standard. There is a framework called sum of histories quantum mechanics. We find them in games, in which they start from that as the beginning, and then we work out the rest of quantum mechanics. Things like transformation theory, other operators, and so forth, are things that emerge, right, as approximations. So, for example, they get momentum from time of flight. I'm taking that standard and ancient point of view here.
But the point is that if you were deciding to choose momentum as your finite path,
I don't think momentum is going to work. You might be able to do a positioning momentum.
You could, right? You could just, you could slice your Hilbert space. Okay. So will you get the same notion of reality?
I don't know. It says in Prime Minister's question time. I refer the questioner to the answer I gave a few minutes ago. I don't know. Right? You can, I mean, there are lots of things to work out here. I did not sort of work them all out. Okay, so come back to reality here. As Weinberg's, now I'm talking about generalization. Forget about all that reality stuff. It's been striking so far, and repeating his quote, but this point of view does allow us, and that seems to me to be the main interest of this talk, to investigate distributions which are close to quantum mechanics without being quantum mechanics itself. That is, we can consider small deformations of the fundamental formula and thereby hope to parameterize experimental tests or maybe even get new insight into a better formulation of quantum mechanics from which even deeper histories would be emerging. In that process, if you start to mess with that formula, you put at risk a lot of features of quantum mechanics that are emergent, right, even in the sum over histories expression. The notion of states at a moment of time won't necessarily exist. Unitary evolution, Hilbert space, linearity, or the principle of superposition. These are features that emerge just by assuming this, and calculation. But if you start to tweak the formula, you can't expect those things to be around. Nonetheless, the theory would be predicted. But in any rate, in quantum gravity, we don't expect to have states evolving unitarily through a sequence of space-like surfaces because there isn't any fixed notion of space-like surfaces because there's no notion of space-time. And in cosmology, it's always been a puzzle to me why we work in a framework which is basically built on the principle of superposition when there's only one state, the wave function of the universe. And so we never need to superpose it with anything. So we may not need these in completely general. Of course, we have to get them back out because of the theory. Glad Raphael Sorkin is not here because this is a little early for him, I think. Yeah. No, I sent him an email. I said, don't come. I know it's early. I'll see you at lunch. Okay, Sorkin has always stressed that a fundamental formulation of quantum mechanics should be based on a set of fine-grained histories and a preferred set of variables. You must have heard him, right? Around here, in which one history is real, right? Here it is. Well, many people have raised outstanding questions, you, which would be interesting to follow up, but here's some other ones. I don't have yet an information theory for this kind of extended probabilities. I think there should be one. So what is it, right? I mean, should be some notion of accessible information and these recorded bets and so forth. But I don't quite, I haven't worked on this, but so it'd be good if you would work this out. And what's so special about this? This looks pretty peculiar when you get down to the end. And there is a problem for Lucian, right? What is so special? If we take this fundamental distribution point of view, what is so special about that? Well, okay. Those are all the same. Here's the main things again. Quantum mechanics can be formulated as a theory of sets of alternative histories in which each history is assigned an extended probability given instructions for having betting on them, including negative probabilities. Don't bet on that. Records of histories can be used to settle bets. Recorded histories have probabilities, positive probabilities, and are decoherent. And thus, on settleable bets, decoherent histories and extended probabilities are equivalent, up to the slop and the level of decoherence. And we recover, if you like, decoherence histories in this more general. Same with Copenhagen quantum mechanics, which is also only up to the slop and decoherence. On the sum over histories formulation, quantum mechanics can be viewed as a classical stochastic theory with a fundamental distribution giving probabilities one history is real, and this formulation can be used as a generalization and in the search for alternatives to quantum mechanics. Don't be afraid of negative probabilities. They give you a new perspective of quantum mechanics that might be useful. Thank you very much.
nice in some sense, but it seems to me this issue of records has been glossed over. What property allows a history to be recorded in some definite way?
Let's take decoherence. Right? I mean, it works the other way around, although I didn't mention it. If a set of decoherent, a set of histories decoheres, there's always a record. And the reason is...
Some of the box.
I would write down it.
Decide to project with the box.
If you have a set of histories, if these are orthogonal vectors, that's decoherence, then there's always some set of projection, right, that will project down on these vectors from the original state, and therefore, in some formal sense, decoherence implies the existence of records.
But is the set unique?
No.
Then what is it that makes one set give me a record relative to some other set? So I have two rocks collide in the woods and I don't know, and I can infer what the history of the rocks was.
So we just calculate from here. So typically what happens, typical mechanisms of decoherence, for example, if you put for example, if you put one particle out in interstellar space, right, in a superposition of two positions a millimeter apart, then in a second, 10 to the 11th microwave background photons scatter off them. They carry away the phase, and in principle, right, you could look at those photons carry a record of what the position was they scattered off of. So it's just a very general formula.
Well, I'm not disputing the formula. It just seems to me that the notion of what a record is somehow hides a mystery that the word measurement hides in other contexts.
It's certainly connected, and typical what we mean by a measurement situation is basically one where the alternative is recorded.
Yeah. So does this help the measurement problem in your view?
What is well, let's not go there. I mean, I don't never believe
So you don't want to go there.
I never believe there is a measurement problem, but I don't know what the problem is. Measurement, I mean, I've been jumping on you for mentioning measurement, but measurement, of course, can be described in this situation. We're considering a closed system, so we consider, the apparatus in the system. We study the correlations between the apparatus and the measured subsystem, right? And so we just calculate. It's just a special case. Then, when a bunch of conditions are satisfied, you recover approximately the usual measurement story. Well reduced. Those conditions are rather special. In general, it doesn't hold, right? I mean, I set out to find what the examples were. I mean, we have a fair amount of examples of evidence for Schrodinger's equation, but I want to know what the evidence for the projection part was. So I started asking various statisticians, and finally, your friend Milford claimed that, as far as he could tell, there's only one, which is blinking atoms, where it actually works. You can project, evolve, and verify that formula. There are not many. Most of the time, for example, if you take a photographic plate, the state of the electron after it gets absorbed by the silver atom is not in an eigenstate of something else. It's bound up in the atom. It's a complicated. So, but all that stuff vanishes in this, where the projections are not measured. In general. Yeah. Good.
Response to that, which I hope you'll like, because it connects up to your expression of reality. So the criticism is similar to one that you can apply to pilot news. There's a certain underdetermination in the model. So I would discuss there's potentially other choices for sets of projections or timing to make.
What universe are you looking for the determinations in? Yeah, so it's under determination relative to some universe of possibility. What's the
I'm saying that you present one model, and I'm saying, okay, here are a bunch of other models that you could have written down.
Yes.
And they'll all give different descriptions of reality.
Mm-hmm.
And so now, if you adopt a methodological principle that I think Einstein sort of promoted, if there's a difference that doesn't make a difference to the laboratory and the experiments we see, then we shouldn't assume it's a difference of reality. So at this stage, somebody can say, well, I don't like your model because there's all these possibilities and we don't see how it makes a difference in reality. But at this stage, a response that's given in the context of pattern waves, which you could also give here, is that if you've extended the model so it no longer agrees with predictions of quantum mechanics, then you can start to distinguish between those different models. So you could say, oh, well, whether it's position or momentum, that's not going to make a difference as long as we stick with these sorts of things. But if I vary the prescription, then all of a sudden it will make a difference, and then we could experimentally go and determine what is the correct equation for the joint extended probability. Maybe it's not Wigner's formula, maybe it's something else, and what's the correct preferred observables to use.
I agree with your statement. I don't think it was a criticism. And I only worked out, one model, right? But my interest is doing exactly what you said, varying quantum mechanics, right? And then seeing, based on some set of frameworks like that, and then seeing what the experimental differences would be.
Do you agree that if you didn't vary it, then there'd be some sense in which you'd be suggesting a set of models, and it wouldn't be clear in what sense you could be committed to one of them?
Many years ago, when I started out on decoherent histories, I expected all work on the interpretation of quantum mechanics to stop. This turned out to be naive. So I'm not saying that here. Right? So I agree. So the theory needs to be elaborated, right? Over it's just exactly as you say. It would be great if somebody could do that. I'm busy with these weird problems in equationary cosmology. But I came here exactly for this. What is your strongest criticism? I got it.
Are you able to apply this to something like, say, hydrogen atom?
Yeah.
What do you get?
Oh, well, I'll get for things like measurements, I'll get the usual answer. Right? I mean, what would the extended probabilities be for something?
What is the electron doing?
Jack, I only got as far as the two-slit experiment. Right?
I mean, it's a real test, right? I mean, if you really apply it.
Two-slit is pretty real these days.
No, but do you differ or not, and so on? If you take
I don't believe
I
get a real different experimental predictions for measurements unless you vary the fundamental distribution.
I mean, you are giving the prescription for what the probability is for what anything is supposed to do.
Yeah.
Like the electron distribution.
The measurements correspond to settleable bets. We bet on the outcome of measurements. So there the theories will agree.
Yes, I've been thinking about your question. So it'd be nice to embed this kind of thing in an even more general framework.
Okay.
So a lot of people recently have worked on this sort of so-called convex probabilities framework, where you represent states by lists of probabilities.
You're among them.
I'm doing one of them, but there's a long tradition in such an approach. So I'm wondering if that would work. Something that's one way to try and get a handle on where something comes from. Then it would be nice in the context of such a framework to sort of come up with a set of axioms or something to show that really this kind of thing emerged.
Yeah, exactly. That's what this. I lost it. Let's do this.
There it was.
Yeah.
Yeah.
It looks okay. In your framework with these lists and everything, does that emerge as a sort of natural?
Maybe. I mean,
natural thing. It's a little bit different, right?
I'm not standing up, but I still don't have definite answers. Yeah.
Well, Jim, what ways have you imagined tweaking this? You said it somewhere a little earlier, tweak this expression. In what ways might you want to tweak it?
Adding other terms.
And then if you answer that, then maybe Lucian can say, yes, this fits in the convex framework, or no, it doesn't.
I just haven't done much, had the opportunity to do much work on this. I haven't been distracted by other things. But, take the action, it has more terms to it. Not necessarily unitary terms. See what quantifies them, see what limits the experiment gives on it.
I see. So tweaking in that case might mean something like making S non-standard or even imaginary or... And presumably other ways of tweaking is take away the reality condition or not, or...
Well,
I mean, so then we have complex probabilities. Maybe I'm being cautious. There are people who would say such things. I agree the reality is like we're in front of us.
Jim, I have to really understand what you're saying about the probability. So, if you are doing ordinary quantum mechanics, you would say, before you take the real part, you would say that this is the probability amplitude from starting from some initial state.
Only for measurements.
But I mean, let me finish, just to understand if I'm saying it right. So, if you don't take the real part, it would be the probability amplitude for starting from some initial state and then ending in some final state, the amplitude. Am I right?
What's
the expression that we have right there.
Yeah, that's right. But in the Heisenberg picture, it's easy to see. There's just an expected value, where the state is the same. So you can say,
right. Because before you take the real part, I would say that's the amplitude for starting from some initial state and then ending in some final state. Is that correct?
well, the initial and final states are not different.
No. If I take psi as my initial state, apply all these projection operators on it, I end up in what I would call the final state.
Okay.
And then dotted with the other side is probability amplitude for starting from some initial state and ending in a final state, in usual quantum mechanics. So in usual quantum mechanics, you would say, if you want the probability, you would take the absolute value squared of that. Instead, you are saying take the real part in your definition of probability. Am I understanding it correctly or not?
Not quite. Because it's not true in the quantum mechanics of closed systems that the square of that gives the probabilities unless the set of histories is decoherent. Or you could say if you have a measured subsystem, that's true, which is a way of importing the decoherence.
Yeah, for subsystems. So.
A measured subsystem, that's it, as you evolve, reduce, and square. Okay. But in a closed system, that's not true because the probability sum rules wouldn't be satisfied. It'd be inconsistent, as in the two-slope experiment. So to deal with quantum mechanics in closed systems, we can't have the usual rule, you just square it, right? You have to have a rule that tells you which sets can be assigned consistently probabilities and which cannot. That's decoherence. Okay. So then I agree. And disagrees with that, as I showed you, right, in the case when the set of histories is decoherent. It's exactly the same. But it extends it when you're not. Other questions? I think my guess is your problem, you're not even with us on quantum mechanics applied to closed systems like cosmology yet. Right? So we'll talk if you're here tomorrow or the next day.
Are there other questions? No? All right. Thank you.
Thank you.